All right, like I said last time, we're splitting section 6 into two parts. Today we're talking about the second part, which is going to be applying rational equations and inequalities to different real-life situations. And to do that, we're going to use something, at least for some of the problems, we'll use something called a weighted average. A weighted average is basically a way for finding the mean or the average of a set of numbers, where some elements of that set of numbers carry more importance or more weight. It's kind of like with your grades. Quizzes and tests weight 85% total. The homework weights 15%. And lots of real-world problems. Today we're focusing on ones involving mixture, work, distance, and even sometimes interest, although we won't see that one as much, can be solved by using a rational equation. So I can set up an equation that involves fractions of polynomials, and from there I can solve. Okay, so we're just going to jump in and try a few of these. And in class tomorrow we will practice. So the first kind of problem we have is a mixture problem. Aaron adds an 80% brine solution, that means 80% salt and water, brine is salt and water together, to 16 ounces of a solution that is 10% brine. So I have some amount of 80% brine that I don't know, and I have 16 ounces of my 10% brine solution. So how much solution should he add to end up with a total solution that's 50% brine or 50% salt? So I have 16 ounces of 10%, and I'm going to add my 80% until the total percent is 50%. Each solution has a certain percentage that is salt or brine, and the percentage of brine in the final solution has to be the amount of brine, so the amount of salt, right? Oops, why isn't that writing for me? There we go. I have to have the amount of salt divided by the total amount of solution. That has to equal 50%, or 1/2, 0.5. All right, so a lot of times when we do mixture problems, we set up a table that helps us to kind of organize ourselves. So the original thing that I know is I know I have 10% salt in 16 ounces of my total solution, right? So notice this first row here is the amount of brine. Remember again, brine means the amount of salt. So 10% of my 16 ounces is salt. The total amount of solution in ounces is 16 here. I don't know how much of my new solution I'm going to have, right? That's what I need to know. How much do I need to add? So that's my x. The amount of salt will be 0.8, 80%, times the amount of ounces that I add to my solution. So here I have my total, right? The total amount of salt will be 0.10 times 16 plus 0.8 times however much I add. And the total solution is 16 plus x, because I started out with 16 ounces, and I'm adding an unknown amount of ounces. So remember, the percentage of brine is the amount of brine, right, so which is this here, over the total solution, 16 plus x. And I need that to equal 50%, right? So I need 50%, 50 over 100, to equal my amount of brine, 10% of 16 plus 80% of however much I add over the total amount of brine. So I simplify that. 0.10 times 16 is 1.6. Now I'm going to multiply both sides by my least common denominator. This is back to like the first part of the video we saw yesterday. I just need to solve for x. So on this side, my 100s will divide out. Here they show you that here, but I'll show you back here too. And I'll be left with 50 times the quantity of 16 plus x. Here my 16 plus x's divide out to 1, and I'm left with 100 times the quantity 1.6 plus 0.8x. That's what they show us here. And then we just have to simplify. So we're going to distribute that 50 and distribute the 100, and from here I just solve like normal. So I end up with 21 1/3 equals x. Remember, x is the amount of ounces of my brine solution that I need to add, the 80% brine solution that I need to add. So Aaron needs to add 21 1/3 ounces of 80% brine solution to the 16 ounces of 10% solution to end up with a solution that will be 50% brine or 50% salt. And we can check, of course. We can plug into 21 1/3 in for our x, and we can see if it works. And it does. If you do the multiplication, both sides end up being 50%. Remember, this represents the amount of salt over the total amount of solution, which gives me the percentage of salt. Okay, here's one for you guys to try. Your answer here is B, 10.4 ounces. And here's all of the beautiful work for that one. It's very similar to the last one in my table. I have the amount of base over the total solution because the percentage base, right, needs to be 40. And I get that by taking how much base is there in my solution over how much total solution do I have. So here I have a column for what's happening in my original solution, what I'm adding, and then the total amount in my new solution. And it's this new solution, the amount of base over the total, that needs to equal my 40% here, or 40 over 100. All right, this time we are going to talk about distance problems, okay? So for these problems, remember the distance equals rate times time. We've done problems like this before, especially in 8th grade. So Lilia swims for 5 hours, so she's swimming for 5 total hours in a stream that has a current of 1 mile per hour. So that's the rate of the stream. She swims upstream for 2 miles and then back to the dock, right? So she has to go 2 miles back to the dock, but when she goes back to the dock, she'll be going downstream, which means she'll be swimming with the current. Upstream is against the current, so she's fighting, the river's going against her. And downstream, when she comes back, she's going with the current, so she'll go faster. So we want to find her speed in still water without the current. So basically what we do is we think about the fact that she has to swim 2 miles upstream against the current, 2 miles back with the current, and I have to remember that distance equals rate times time, and I can rearrange that equation in any way I want. In this case, we're given some information about time, so I'm going to solve my equation for time. Distance over rate equals time, and I'm going to use that to get my total time of 5 hours. So let's look at how we set this up. First of all, we define our variable. So R is going to equal her speed in still water. So her speed with the current will be faster, right? When she's swimming with the river will add 1 mile per hour to her speed because that's the current of the river. When she swims upstream against the current takes away 1 mile per hour from her speed or from her rate. So her time going with the current, remember this is distance over rate equals time. So this represents a time, a distance of 2 miles over a rate with the current of r minus 1, plus a distance of 2 miles, because if she went 2 miles away from the dock, she has to come 2 miles back, over a rate of r plus 1, because she's going faster when she comes back with the current. And remember, both of these represent times. My total time is 5 hours. So we're going to solve this. Let me erase all of my writing here, sorry, so that you can kind of see what's happening. My LCD, this is my original equation. My least common denominator will be r minus 1 times r plus 1, which is r squared minus 1. That's how they're showing you there, but it's really r minus 1 times r plus 1. So when I do my canceling or my dividing out, I'm left with r plus 1 times 2 plus r minus 1 times 2 equals 5 times r squared minus 1. Don't let that confuse you. Just remember that r squared minus 1 is r minus 1 times r plus 1. So I get this. I eliminated my fractions like we do when we solve rational equations, and I distribute, and then I simplify. So I end up with 4r equals 5r squared minus 5. I get my 4r over to this side, and now I have a quadratic equation to solve. I'm going to use the quadratic formula here. It's a good way to remember that. Negative b plus or minus the square root of b squared minus 4ac all over 2a. If you don't know it, you need to. And I just plug in my information. A is 5, b is negative 4, and c is negative 5. In this case, my x, or my variable, is r. So they just replaced x with r because I'm solving for the rate. And when I simplify this, I get two different answers. 2 plus or minus the square root of 29 over 5. And when I use a calculator, I either get 1.5 or negative 0.7. Speed has to be positive, right? We're not going to talk about her going negative miles per hour. So her speed here in this case was 1.5 miles per hour in still water. So when she goes with the current, she would be going 2.5 miles per hour. And when she goes against the current, she would be going just 1/2 of a mile per hour. So we're going to check that, make sure it makes sense. Here we're just showing you plugging in 1.5 for R. And this is an estimate because remember that these up here, 1.5 is not exact, 1.5 was an estimate. So we get something pretty close to 5. So that means that our estimate was pretty close. All right, you guys try this one, another swimming one. Your answer here should be D, which is about 6.6 miles per hour. All right, here's the work for getting it set up and getting down to a quadratic equation. I'm not showing you the work here with the quadratic formula because you should be able to do that. I feel like the hardest part of these is usually setting them up. So again, remember we have distance times rate equals time. Oops, sorry, I said that backwards. Distance equals rate times time. So since I know something about total time here, I want each of my terms to represent time. So I use the formula. Time is distance over rate. So 3 hours upstream against the current, so she goes slower, so her rate goes down by 2 miles per hour. And then her distance back to the dock, 3 hours, she goes faster. It adds 2 miles per hour to her rate. All of that together in 1 hour. So that's how we set that up. All right, last kind of problems we're going to see here are work problems. So here we have a mowing lawns problem. Wui and Uima, I guess that's how you say that, mow lawns together. If Wui works by himself, he could do one job, one lawn, in 4.5 hours. Uima could do it alone in 3.7 hours. So if they complete it when they work together, how long, so again, we're looking for a time, how long will it take them when they work together? So we know that Wui, if that's how you say his name, can mow the lawn in 4.5 hours. So his rate is 1 lawn per 4.5 hours, right? He does 1 lawn in 4.5 hours. So that's his rate. Uima has a different rate. She can mow 1 lawn in 3.7 hours. So that's her rate. The combined rate would be 1 lawn, and we don't know how long it's going to take them together, right? So we're letting X be the amount of hours it will take them to mow the lawn together. So this is the rate, Uima's rate, Wuyi's rate, and that's the combined rate. So these two rates added together have to give us our combined rate. So I set that up, and I just solve. If you get confused with these fractions that have decimals in them, I would just multiply the numerator and denominator of each fraction by 10. Multiply this by 10 and by 10, so that would give me 10 45ths plus 10 37ths has to equal 1 over x. That's where they get this fraction, is from the common denominator between 45 and 37. And then I'm going to solve for x. Here they're multiplying both sides by x, basically. So I multiply this by x and this by x. And then I have to get x by itself, multiply both sides by that reciprocal, and I get about 2.0304. So what does that mean? It means that together it would take them about 2 hours to mow the lawn. So one of them by themselves can do it in 4.5 and the other in 3.7 hours. Together they would finish the job in about 2 hours. And if I check, again I'm estimating because I estimated that too, I do end up with something that is pretty close to 1/2 is equal, or approximately 1/2. Alright, last one here, try this. In this case we get C, about 2 hours and 45 minutes. Here's the setup for this problem. 1 over 6.4 is Adriana's rate. And Monique's rate is 1 over 4.8. So if I add their rates together, I should get the combined rate. From there I just solved. I got about 2.74 hours, which is about 2 3/4 of an hour. That's where